All right. So this will be the last hour for this course because next week cover from lecture 1 to lecture 5. And lecture 5, actually, I don't think it is possible to finish all the contents today. So the coverage was until the place we stop today. And the same as the midterm, like we will have 2 classrooms and then we will announce the seat table later. And like if you have some time, please help to fill out the course evaluation form because like it would be great like if the course evaluation form can be filled more than like 60 to 70% of you. Okay. And next semester we will have another course that is about the memory and storage system. Just like if you are interested in, just feel free to join with us. Okay. Okay. So before we start, let me briefly do some clarifications. So actually there are some very valuable questions last week and I go back to check about some contents and I think there are some things I need to do like clarifications. So first of all, it's about the cache miss. So last week we talked about patch cache. It's about to read a file from the storage device to the memory and store in the patch cache. But the problem is like if the file is not in the patch cache, then there is a miss, right? So in this way, is it about to use a patchful handler to handle it, or like is it any other ways to handle it? And after checking the kernel, actually it is not about a patchful handler. I mean, even patch cache is in the memory and it is related to the patch, but it is not using a patchful handler to handle it. It is about to use the file system handler. So just like file system handler will sense the BIO structure to get the missing data. So it is about file system will take care of it, and then the patchful handler, it is more related to the memory management, so it will not really involve inside to take care of this patch cache messes. Okay. So there's a second clarification. Says I think maybe it's last week or like maybe in past 2 weeks. Actually we're talking about the log structure file system, and we said like log structure file system updates checkpoint regions in a periodic way. But actually, after I check in about some like information, actually it is about there are several cases for triggering the update for the checkpoint region. And usually there are 2 ways. One is a periodic update, and that is about when the log structure file system is going to do the segment cleaning, then we will do the update. So it is about like how often the segment cleaning is triggered. So it is a periodic way. And the second one is about the immediate update. For example, if we are going to sync the data from the memory back to the storage right away, then for example, in the user process, we will call the file sync, the fsync functions, and the fsync system call will directly write back the data from the memory to the storage. Okay, so I think it is not easy to understand. So let me do some animation here. So like we have a write buffer, and then there is a part like we say like inside the write buffer, there is a fixed size continuous region. It is called segment. So usually like the size of segment is defined by a different log structure file system. So you can image, for example, if the segment size is 4 kilobyte, then inside the write buffer, we need to add this to accumulate to up to 4 kilobyte. So we can write back the 1 segment back to the hard disk drive. Okay. So we just assuming now this is a segment. So the segment will be right back to the hard disk drive at the same time. Okay. And the case is like this. Oh, sorry. This is just about to let you know inode for like the first data and the second data. Like what's the relationship? It's not quite important here. So like if we now update DJ, I mean the second data chunks of DJ, like here, if we update it, actually because this is a log structure file system, so we'll first write into the memory, not directly modify it inside the hard disk drive, right? Because it will be super slow if you directly modify the data in the hard disk drive. So we'll only mark the data in the hard disk drive as an embedded data by using some data structure in the memory. Okay, and the case is like if we're going to update this DJ2, and it probably means like we need to write the DJ2 to some other places. because this is a log structure file system. So we will not directly write the data back to the same position. For example, it is a log structure, so we will log the data at the tail of this hard disk drive, right? So in this case, inode should also be updated. So inode here, like the third one, this data block should be updated to the new location. Okay, so you can see now there are two embedded data inside the hard disk drive. This is the embedded data. We use a dark gray color to color it, and this is also the embedded data. So if there are a lot of updates occurs in the log structure file system, then there will be a lot of embedded data. And segment cleaning is going to use to clean out those embedded data in a segment granularity. What do I mean is if we are going to do the segment cleaning for this part, then we will read out this whole segment. We'll read out the valid data inside these whole segments into the memory, and then we will merge with the data in the write buffer and then write it again to the hard disk drive. So in this case, we can remove this embedded data here. So it should be in a segment granularity. So it is very similar to how SSD works to do this kind of garbage connections. So this is called a segment cleaning. So the time to trigger this segment cleaning, actually, it usually like maybe every 10 microseconds or like 10 seconds, the system will trigger it once. So this is about the periodic update part. Okay. So this just want to let you know, actually, there is the reason like LFS also needs to update in a periodical way. Okay. All right, so let's move on to the Q&A part. So actually, there's a lot of interesting questions, so I just arrange out here. So one question is from the block layer. Like last time we talked about the block layer, like we do some introduction on the sector, block, buffer, those kind of terminology part. And I slightly modified the figures to let it, I think will be better for you guys to understand. This is a storage device that we have now, right? Then we say on the storage device, there is a granularity called sector. So sector is a power-related granularity. Usually it is 512 byte. Okay. So there is another thing is memory. When we are going to access the data in the storage device, we need to move it to the memory. Okay. But the thing is like this. In terms of the file system, actually, there's a thing called block. So in the point of view of the file system, actually file system doesn't really know what is sector. So the minimum access granularity or like the minimum allocation granularity for the file system will be a block. So maybe block is a little bit not really familiar with for this terminology, but you might hear about something called data blocks, right? When we're talking about file system, there's data block, there's derivative blocks. So those blocks is the same thing like here. This is also called a block. They are the same. Okay. So the size of the block is also a fixed size, but usually the size will be larger than a sector. So usually in current file system, we will use like 4 kilobyte as a block size, or maybe 8 kilobyte. Okay. So this is called a block. And then if we're going to access this block should move into the memory. So then the block will become a buffer. And the buffer is the things that we talked a lot last week is about cache. So cache is a combination of several buffers together, and this is called a cache. Okay, so you read the data blocks from the storage device to the memory, and the place to put this buffer, they are called cache. Okay, so this is like to, I think this is a way to answer some others that like a lot of you guys asked about like what is the relationship between the block and buffers. Okay. Okay. So following on, the second question is about does log structure file system still have an inode table on the disk? So before answering these questions, let me do a quick recap. We say in the file system, like on the disk, usually there are several components here. There are boot block, there are super block, and also there are inode table and their root directory. Okay, so I think this is not super precise because the inode table here, what I'm going to show you is about, this is just a concept, but different file systems will use different data structure to implement this inode table. So for example, in a log structure file system, we use the inode map to organize the inodes. And for example, for ext family file system like ext2 to ext4, they're using centralized fixed size inode table. So this one is the same as what drawing in the figure for this one. Inode table is contiguous and then it is a fixed size. Okay, so actually this one are widely used in the ext family. But there are also some other ways for this kind of inode table implementation. For example, for XFS, BetaFS, ZFS, those kind of file system, they're using B-tree like structure. Okay, so this is just a conceptual, like to let you know, actually there's an inode, like there's a way to organize the inodes on the store device, but it depends on the implementation of different file systems. Okay, so after finishing talking about the file system part on the disk, actually last week we were talking about the virtual file system. So when we're talking about the virtual file system, we also talk about actually the inode and the entry objects, all those kind of objects, actually there are inside the memory, not on the storage. Okay, so maybe you'll be curious about like what is the data structure for inode object in the memory. So actually there are several kind of possibility. And the most like basic one would be the linked list. And then there are also like hashing and registry. So both hashing and registry is help to quickly find out the inode object that like the request is requiring for. Okay, so this is about actually the data structure for the inode object in the memory and inode, and the data structure for the inode on the store device actually has slightly difference. Okay. Okay. So there is another question. It's about like the de-entry object. So because like we say, actually there are there's a set state for the entry object is called unused, and the statement is like this: like when kernel evicts a file from the patch cache, it may remove the inode object, but will usually keep the de-entry object. And this statement is correct because like usually we use the inode object to describe the data inside the patch cache, to describe the data block in the patch cache, right? So if we remove a file, then it means like we are going to remove the data blocks correlated with this file. So the inode object usually will also be removed, usually. And the entry object is about the path for this file. So it doesn't really need to be removed that fast, because it is just about the file path for this file. So it doesn't really highly linked with the data content part. So what I'm going to say here is actually the entry objects and inode objects, actually there's no very close, I mean like correlation between each other. One of each of them can be stay inside the memory. They don't really need to be evict out together. All right. So here's also a question is about the virtual file system and the inode object and the entry objects. So actually, when the user sends the MAC directory or like some open functions, this kind of file operations to the VFS, actually the VFS will create both the inode objects and the entry object. Okay, but the VFS will not create a file descriptor while serving the MAC directory, because the MAC directory is going to create a directory. It is not about to open the file. And the file descriptor only be used when you are going to interact with an open file. Okay, so this is the things to let you know. Here are some a little bit tricky things here, because like MAC directory actually don't really open anything. It is about you create a new directory. Okay. Oh. The difference is about you say you're going to create a directory, but you don't really use it at this moment, right? You only create it. But for the open file, it's about you're going to open a file and you are going to write data inside the file. Yeah. So this is a different. And the file descriptor is used for when you use the open command, like in your C code, you say you're going to use the fopen. So the fopen will open a file and you can interact with this file. So it's a little bit difference between each other. Okay, so there is another question, and I think this is a super good question. But if you still remember, we have this kind of structure, like we have the file descriptor table, and there's open file table and inode table. And we say when we are going to open a file and when we are going to interact with the file, we will walk through this path, right? But the thing is about, well, there is no entry object in the following figure, right? There is only open file table and inode table. There is no entry object here. So actually, the reason is this figure is going to describe about when a file, after a file is open, and how the file descriptor can access to the data. Okay, so the assumption for this figure is about the file is already open. And the entry object actually is about to resolve the path. So like you are saying, like if you are going to access the data from which directory, and it must go from start from the root, right? And the entry object is going to help to resolve, okay, so where is the data, where is the file is. And if the file is already open there, then we don't really need the entry object to do the file path resolving again. So this is quite different. When we say we are going to open a file, actually you can think about there are two steps. One, you need to first resolve the file path. Otherwise, you don't know where the data is, right? And the second one, after you resolve the file path, you get a file, then you open the file. Okay. So there are two different things here. And this one is about after you get in the file path, then you can open the file. And this is the figure for that one. And when we're going to accelerate file path resolving, and we say actually I think it's at the last week, it is about we introduce the file path resolving. It's about actually we loop through the entry objects, and if there is already in the memory, then we can reuse it. If there is no, then we will run the path resolving by doing some operations inside by using this entry object. Okay, so once again, when you are going to open a file, but the file is still not in the memory, the first thing we need to first check about if the file path is resolved already. So we'll first check about the file path resolving. So if the file path resolving is finished, I mean the file path is already there in the memory, and then you can go for this one. You can go to open the file. Okay, so this is two different things. All right, so after actually there are a lot of very good questions, but I think it is hard for answering all of them. So those are the things that I think it is so critical for the this course. And then let's quickly do some recall before jumping into the patch cache. So VFS, I think you already get some feeling about it. It is between the file system and the user space kind of code. Okay, and VFS is going to serve for the users if the user do not want to deal with a lot of different kind of file systems. So it is a unified interface for users. Okay, so actually there are four primary objects there. Superblock is usually describing the mounted file system. So it is about how this file system look like and how, like for example, what is the block size for this file system, and like is it using the inode or maybe it is using what kind of data structure for this file system. And then we have the second one is like inode object. So inode object is about how to describe a specific file in a metadata perspective. Because like we say like a file means like there's a data contents, But in addition to data contents, there are also like permission. There are also like the how to access a file, like where is the file stored in, like in the storage device or in the memory, this kind of stuff. So those kind of metadata, we use inode object or like the inode to describe it. Okay. And the same things, because not only the file, like directory also related to the inode. So usually inode object is going to describe both the file and the directory. So the third one is the entry object. This is quite tricky because the entry object is going to represent a path, just like how to quickly resolve a file path. Okay. Sorry. And the fourth one will be the file object. So file object is quite simple. It's just like when you are going to open the file, then there are several things that you are going to use for opening this file. So this is about the file object part. Okay. Okay. So I think that the entry object is a little bit hard to understand. So I'll do a recall for this part again. So because the current file system, they're using the hierarchical nature, like there is a directory tree. So from the root to the directories, and there are several layers of directories, and then at the end of the directory trees, you can find your file there. Okay, but the problem is about actually each directory is also stored inside the directory block. It is also stored inside the data blocks. So we need a way to quickly know where is the directory stored inside the store device, right? So actually, this is what directory entry is used for. So there are a lot of things, but I think what I can think about is, I think this is a better way to let you know what is the entry. Actually, it is a mix between the inode and directory entry. Okay, so actually, sorry, one moment. I think this one is better to understand. So what I say is a mix between the inode and the directory entry, because actually inside the directory entries, it only stores the inode number and the corresponding file name, right? So for the entry, actually, it includes the file name in the directory entries. But actually, if you only use the directory entries, you cannot get the data, right? Because inside this data structure, there's only inode number and the file name, and there is no pointer to the inode. So if there is no pointer to the inode, you cannot get the data. And the entry, actually, there is a pointer to point to the inode object. So it is easier for the system to get the data, because using the inode, then you can get the data no matter from the pad cache or from the storage device. Okay, so you can think about the entry just a mixed structure between directory entries and the inode. Okay. Okay, sorry. So let's go back to the first place for this patch. So actually this patch is about to let you know like how to do the rename. And the reason like we are going to explain the rename is because rename is quite complex enough to let you know how VFX works too. So by Linux, actually when you are going to run rename, it's going to replace the entry with a new one. And not only the entry, also the directory entry should also be replaced with a new one. Okay, so both the entry and the directory entry should also be created. So we said the issue is about like it's quite intuitive. Why not directly modify the name in the entry, right? Because inside of the entry and inside of the directory entry, there are no file name there. Why not just directly modify it? So there are two reasons here, but today I think I will only focus on the first reason, the consistency issues here. And the reason is quite simple. It's because if we directly modify the name in the entry, actually this is not atomic. Okay, so this is a toy example here. So here is a storage device, and there is an inode table, and there is a directory block. So inside there are directory entries. Okay, inode 4, and what is the file name for inode 4? Sorry, inode 4, and what is the file name for file 1? And inode 5 is for file 2. So what is the file name for file 2? Okay, So inside the entry, so inside the memory, there is a D entry. The D entry is about if we are going to get a file, the data contents related to file ones, then we need to first know what is the path for the file ones, like from the root to this file one. So the entry can record the path resolving result here. And also inside the entry, actually there is a pointer pointing to the inode objects inside the memory. Okay, so by using this inode object, we can get the data from the patch cache. So this is the data, the data contents for file one. Okay, so if we are going to update if we are going to rename file one, and if we directly rename it in the D entry, and here is the issues here. If we update file names in the memory, and for the consistent issue, actually we need to write back to the derivative block, right? But the issues here, because storage device is super slow, and if we are going to write the data from memory to storage device, actually if there is a power failure or maybe your file system crash in between when you are writing the data, actually there will be a partial result. So for example, if the file name in the D entry is from A to Z, for example, there are 26 alphabets there from A to Z, okay? But when you are writing back to the derivative entries, maybe when the system writes to maybe A, B, C, D, maybe writes to D, and there's a crash. And at this moment, actually, the derivative entries will only keep A to D, not A to Z. So when you recover the system, it's actually all the things in the memory, they are already scratched, right? There's nothing in the memory. So only in the file system, and the file system records about actually file one, the name for file one is ABCD. But actually the new name is like you give it as A to Z. So there is an inconsistent between the file system and the user. Or like you can think about is inconsistent between the storage and memory. Okay, so this is because storage is so slow, so you cannot make sure this operation is atomic. Atomic means like this operation cannot be affected by any other vectors. Okay, so so a right way to do it is let's just create a new D entry inside the memory. So we have a new name for file ones, right? We give a new name to the file ones, and then we can invalidate the data, the old D entry in the memory, okay? And then we can write back the new D entry to the derivative entries. Okay, so this one can be atomic. What do I mean can be atomic? Storage device is still slow, but we can make sure, like if there is a crash, then we can still recover back to the prior name. Okay, so because we don't really remove the prior names here. File ones, the old name for file name is for file one is still there. Okay, because we are using append. We only append the new D entry at the tail of these derivative entries. So we will not really in place update the prior name. Okay, so in this case, this can be atomic, like all or nothing. Either you success or like you can roll back to your prior name. Okay, so this is like how to make sure the consistency. Okay. Okay, so I think there's another reason here, but let me jump it. I think this is quite intuitive, so I think you guys can figure out how it works. Okay, so then the path resolving. Okay, so resolving the path is quite important because like inside the storage device, actually there is no path concept there. There are only 30 entries, but like how to construct this directory tree. Okay, so for example, if a user process replaces a file and the file is put in this kind of direct file path, /path/2 and /file. So path and 2 is 2 directories, and there is a root directory. Okay. So VFS first parse to get the root, the path, and 2. There are 3 directories and 1 file. Okay, so there are 4 components here. Okay, so we're going to resolve the path for each component. Okay, so first of all, we're going to check whether the entry of the component is existing or not. And because the root is always there, because the root will be added into the memory when the system boots. So the root is always there. Okay, and the root is for the starting point for us to, or no, sorry, for the VFS to work the path. Okay, so the second one, if the path directory is not inside of the memory, so the entry object is not created, then VFS will run the inode operation, the lookup. Sorry, we will first look up if it is created or not, and if it is not, then we will create a new entry for this path. And how to create? Come to think about, because this path, this directory is under the root, so we can use the root pointer to point to the inode object, for example, like this. This is a root, so we will get the inode pointer for the root directory, the D entry. So the root inode will point to the root inode object. So we can read out the data blocks belonging to the root directory. And inside this data block, actually, this is a directory blocks. So you can think about there is a directory blocks, it means across the root. And under roots, one of them will be the path. Okay, so we can read out the path and we can know, oh, actually, the path is in which is related to which inode. Okay, otherwise you cannot really know. So where is the path, right? Okay. So coming back. Sorry. So after getting this path, you can once again check with the entry object is there 2 inside this entry object? So if there's no 2, then you can go back to once again to check about, okay, so where is 2? So you can use the entry object and then to go to the inode object and then to read out what is the inode for this 2 for this 2 directory. Okay, and at the end you can get the data. Okay, you can get the file where the file is in the data blocks. Otherwise you cannot know where is the file, right? Because given you have this file path, but you don't know where this file really stores inside a patch cache or even inside a disk. So this is about important for this file path resolving. Without resolving the file path, we cannot get the data blocks out. Okay. Okay. So those are about the virtual file system, and then And then next week, actually, we also briefly talk about patch cache. And the key idea for patch cache is about to store the data in the main memory. Otherwise, you need to, every time you need to go to the storage device and get the data, and you will be time consuming. Okay, so there is a file in the storage device, and if we can move it partially into the memory, actually, each time when the file is accessed by the users, we can directly get the data from the memory, not from the storage. So it is about the performance optimization. Okay, so I think I'll skip this part because like this part is just to let you know when there's a read request and how to get the data from cache. So here, and this is for a write operation, so it's the same things. Oh, sorry, I think we stop here. Okay, so for write, actually there's a little bit difference for read because for write there are 2 different options for a write path. The first one is called write through, because I think when you are learning about the cache, there are also 2 steps for write. One is write through cache, and another is write back cache. So write through cache is about to automatically update both the memory cache and the undisked file at the same time. Okay, so when we are going to update the data in the memory, if it is a write through, then we will also update the data inside the file, inside the storage device. So we can make sure both the memory and storage, they are in the same and latest version. There is no mismatch version here. Okay, so this is the write through. Okay, So the benefits would be it keeps the patch cache and storage coherent. Okay. There is no dirty bits needed in this case. And there is another case it's called write back. So write back is the backend storage is not immediately updated. So like this, write back is we first write to the memory, and then we stop here. We don't really write it into the storage at the same times, because we can write into the storage maybe when more data they are accumulated in the memory, or maybe we don't update because maybe after several minutes later, maybe the file is deleted. Then maybe you don't really need to write into the storage device at this moment. Okay, you just need to commit the version into the storage device. Okay, and in this case, you need to the system needs to mark out the patches as dirty or unsynchronized, and then it periodically write those dirty patches back to the storage device. Okay. And the benefits is data can be coalesced and written back in a batch. So just like log structure file system. Okay, so log structure file system can work is because they are using this kind of write back reactive scenario. Otherwise, if there is using the write through, then there is no chance for them to accumulate the enough data inside the memory. Okay. So this is a whole picture for the patch cache. And for the history, actually, before Linux version 2.4, actually, there are two different things. One is called patch cache, and the other is called buffer cache. So patch cache is an interaction with the VFS, and buffer cache is going to interact with the disk. So you can think about patch cache before it's about file and the data inside the memory. And buffer cache is about the data in the memory and the disk. Okay. So because the reason is like actually in the disk, actually you can see like there are different mappings here because each, if you still remember, the block size for the file system usually is 4 kilobyte, right? Which is mentioned in the very first slides. And 4 kilobyte is quite larger than 5 kilobytes, usually called sector in the disk. Okay, so you can think about there are actually add sectors can be combined in one block or like one buffer inside the patch cache. So we can map them by using the buffer cache. But actually after Linux version 2.4, they merged patch cache and buffer cache together. So now there's only patch cache. But I mean, due to the compatibility, actually in current Linux, there's still buffer cache there. But usually when you are going to integrate with the patch cache, they will do all the things that buffer cache can do. Okay. So this is about just to give you a whole picture for the patch cache. So here comes the data structure part. So actually, like for each inode, actually they have their own patch cache descriptor, and we call it address space. So what do I mean for this one? Inode means it is going to describe a file, right, in a storage device. So when one day this file is read from the storage device to the memory, and we call it to write into the patch cache. And we need some way to know, so where is the location, where is the address for this data in the patch cache, right? So this is using the patch cache descriptor. And this patch cache descriptor is per file. So each file has their own descriptor, okay? And then this is a patch cache. So patch cache is quite huge. And then if we are going to know like, okay, so what's the mapping between the file and the patch? Then we need to use this patch descriptor to run through the registry. Okay, so actually like now, I mean the latest Linux version, I think it's after 4.9, something like that, and they're not using registry now. But I mean before the Linux version 4.9, they're using patch registry. So I think it's just about the switching between one data structure to the later one. So I think the registry is easier to understand. So I just put registry here to explain how it works for you guys. So the question is, okay, so if you get a file, then if you are going to access this file, then where is the file stored inside the patch cache? Because the patch cache is quite huge. Usually there are several gigabytes here. And the file size is, I mean, it depends. Right? Maybe some file is small, like only 4 kilobytes, and maybe there are some files is gigabyte level. Okay, then this is how we maintain. So first of all, we need to get the patch index, or we call it logical patch address. So actually, we can always get the file offset, right? So in the file object, there is a file offset there. We can know if this is a huge file, and if we are going to start from which position of this file. For example, if you are going to store a movie, a Titanic, in the storage systems, but you're not going to start from the very beginning. Maybe if you are going to start from the middle of this movie, then the file offset will be moved to the place you are going to seek. Okay, so you can think about it's a starting point for a seek point. Okay, so with using this file offset, we'll first divide by the patch size. Then we can know the patch index, right? It's like a patch is 4 kilobytes and file offset is about in which address. So file offset divided by patch size, you can know, okay, so this this position of this file offset is now in which patch, and we call it patch index. Okay. Okay, so given this logical patch address, actually, we can start to walk through the radix tree. Okay. So radix tree structure is like this kind of stuff. So we start from the root. Like the root, actually, we'll first check a chunk of the bits. For example, if there are 8 bits, like we are going to parse, then for the root, for example, if there are 4 bits, then we'll first check about the first 4 bits. And in this example, I think this is kind of, okay, there are 6 bits here. So for the first node, actually, we'll first check the first 6 bits about, so what is the first 6 bits? So you can see about, here are 2 to the 6 slots here. So we will go for the slots that they are for this logical patch address. Okay, and then the second, for the second label, actually it is about the following, like 6 bits. What does it look like? Okay, so maybe it is not easy to understand. So here is an example. If the patch address looks like this kind of stuff, like there are a bunch of 0, like 12 zeros here. So it looks like this. We'll go through the first 6 bits, and then the later on, it is also another 6 bits. So we will reach this patch. Okay, and then for this one, if the patch address is here, and then the logical patch address will go through the same slots as the first one, because the first 6 bits are all 0. And then we'll go to the second label to find, okay, so where is the 5, 0, and 1, and the last bit is 1. So it is the second slot. So the second slot will point to this patch. Okay, so with this one, with this wave, with this registry, we can quickly position where is the patch. Okay. Okay, but actually, this is not super accurate, because in Linux, this is not about to directly access a patch. Actually, this will be replaced by the patch descriptor. If you still remember, the patch descriptor is going to describe the patch frame, right? So this is the logical address here, logical patch address. Then after going through this radix tree, we can get the corresponding patch descriptor, or we can get the physical address for this patch where it is. And then there are also several kind of fields we can access. For example, if this is a dirty one, or like if this is something like, is there any other like data shared with you, this kind of metadata stuff, we can use this patch descriptor to get more kind of informations. Okay, so this is the way, like if we are going to get the data from patch cache, then we need to first go through the patch registry, and then we get a patch descriptor, and we can know, okay, where the position, where is the address for this patch. Okay, so this is how it works like. Okay, so it will be replaced by all this kind of patch descriptor. So the pointer to the patch descriptor. Okay. Okay, I think we still have some time. So if we briefly put it all together, so you'll see something like this. So at the very top here, actually it's about a process will get a file descriptor while opens a file and while the process is going to do some file operations on it. Okay, so when we call a open, open, then we'll get a file descriptor. And then, so each file is described by an inode. So like actually, usually like if one files there are unpatched in the patch cache, but we only have one address space to map to one file. Okay, because like the file size, as I say, it depends. Maybe some files will be super large, so it will be aligned with the patch size. Because patch cache, the name for patch cache is because you use the patch capability to manage the file. Okay, so for this one, if we are going to get a data, then we will access the patch cache to check about like where is the data is. Okay. Sorry. Okay. And then after getting the patch descriptor, actually the patch descriptor is called a structure patch. If you are interested in, you can go back to the prior lectures. They're talking about the patch frame part. Okay. So with using this structure patch, actually it is possible to link to a buffer descriptor by private, something like that. Actually, I think this is not quite important. Just want to let you know it is possible using this structure patch to get the data inside the patch cache. I mean, there is an address, so you can directly get the data in the patch cache. Okay. Okay, but the thing is about if the data is not in the patch cache, then we say there is a patch cache misses, right? So for the patch cache misses, we can use the buffer structure to get the you can use the buffer descriptor to get about so where is the data inside the store device? So there are two options. One is buffer head and the other is BIO. They're all about the block layers. So like if you are using the BIO, then the file system will send the BIO request to the block layer. So block layer can get the data for it. Okay, so this is to link from the file access to the patch cache and then to the block layer. So if there is a miss, then we'll rely on the block layer to help to get the data from the block device. Okay, so this is about a quick summarize for these things. Okay, so once again, actually, this one like the b-data, the b-patch, the private, actually this is not important. I mean, what I mean for not important is still not be on your final exam. I'm just to let you know, actually, if you are interested in, you can go into a Linux code and then you can see there are all these kind of parameters and you can trace the code. But there will not be your exam to ask you about like what is the meaning for the b-data stuff here. Okay. So I think there is another interesting stuff that you know is about. So we have the patch cache, but how to do the evictions for the patch cache? So ARU, the least recently used strategy, is a good fit for most of caches because like it assumes recently accessed patch would be reused recently. So if we always evict the least recently used patch, then we can get a good performance, right? But here are some issues for ARU. So come to think about it, here is the patch list. So here is from patch 5, patch 6, patch 2, patch 1, 7, 3, 4. And now if we access patch 4, and because it is access, so it will be moved to the head of this ARU list, right? Because it is access. So we can move into the head of this ARU list. Okay. And then you can see like the left-hand side is hot because it is recently accessed. And the right-hand side is cold data because it is list recently accessed. Okay. So when we are going to evict data, we will evict from the tail, or like we will evict the patch number 3. Okay. So this is a very brief concept for ARU, but what's the issues here? First, there is an issue called only use once failure. So the scenario is like this. If patch 4 will only be accessed one time, and because we access the we access patch forward. So patch forward is moved from the tail to the head. But if there only access, I mean, if we can know the whole access pattern and then patch forward only access one time, then actually patch forward is a code data in terms of the whole memory access, right? But at this point, actually, we cannot predict the future. We cannot forecast the future. So at this point, we move the patch forward to the hot area. Okay, so this is the first issue. And the second issue is about expensive overhead for adjusting the LRU every time when a patch is accessed. So here comes a question here. What kind of data structure are a better fit or implement the LRU? So let me give you an example. If now the patch is, the access patch is patch 6, okay, but how do we know where is patch 6? I mean, if the list is super long, then a way to know where is patch 6 is we need to search for patch 6 from the head to the tail one by one. So if the list is super long, like if the list is like million of patches here, then we probably there's O(n) time to search a patch inside this list. And this is only just for one access. For example, if there are 10 access here, then you need to walk through the list for 10 times. So it is super expensive for implement the LRU list like this. So there is a thing called pseudo LRUs. Actually, Linux doesn't really use the accurate LRU. It follows on a two-list strategy to implement a pseudo LRU. The pseudo LRU looks like hit list. There are two lists here. One is called inactive list and one is called active list. So these two lists, they are very similar to LRU, but they are a little bit different. So the thing is like this. For active list, it comprises the patches just visited or like just accessed. And for inactive list, it comprises patches not accessed for a long time. So you can think about active list is a hot list. Inactive list is a cold list. Okay. And then the reference in this figure is about when the data is accessed. We call it when the data is reference. So like if the data is in the inactive list and if it is referenced, then we will move it to the active list, right? Because the data is cold, and if it is getting accessed, then it becomes hot. Okay. And then in this active list, actually, if the data is in the tail, then if one day the data is accessed again, then we will move it to the head. So actually, the head of the active list is the hottest place in this two-level list. Okay. Okay. Sorry. So I think the reason like it is called pseudo is because patch are checked reference or not periodically. So what do I mean for periodically? Actually, in two-list strategy, for each access, CPU will not really go to the list to find, okay, where is the data is. Actually, if you still remember, when we are going to access each patch, we need to walk the patch table, right? So inside the patch table, there is a bit called access bit, and there's only one bit. So the CPU will set up the access bit when CPU doing the address lookup. And then the reason I said it is doing periodically is for each, like, I think it's microsecond level. Yeah, there are few microseconds for every few microseconds, CPU will walk through the whole page table and then will collect all the patches that are set. So in this time region, I mean, several few microseconds, if they are like hundreds of patches that are getting accessed, then those patches are called hot patch. And CPU will go to maintain this two-list strategy after checking this hundred of patches, and then we can update it at the same times. So CPU will not really update this pseudo LRU one by one when the patch is accessed. It is about CPU will update it every few microseconds. Okay. So quick summarize for the texture pool. Actually, like I think this IO stack you are not really unfamiliar with, because when you type about a Linux IO stack in the Wikipedia, like you can see this figure. And I'm just going to let you know, actually, we go from the very top to the bottom and you learn most of it. So from the application level, actually, we learn the system code, like there are all system codes, right? There are all like read, write, and make directory, those kind of, there are system code level, and you already learn it. And then you also learn about the virtual file system part, like their file descriptor, inode map, sorry, inode object and the entry objects, they're all here. And you can see like VFS is connected with the patch cache. And the patch cache is connected to the block IO layer. And this path is about when there is a patch cache miss, then the patch cache will interact with the block IO layer. Okay, so this is about the patch cache. And then for the block layer, actually it is about for the descriptor for the buffer. For example, if the data is not in the memory, then where is the data in the storage device? So there is a bridge between the storage device and the file systems. Okay, so block layer, there's a buffer descriptor, buffer head, and BIO stuff. And then also we learn about like there are several devices here. There are hard disk drive and there are solid state drives. Okay, so yeah, I think let's stop here and call it a day. So this is all about our operating systems. So thank you guys for joining with us. Okay, thank you.
这样子说，它回来可能，可是后面这边有说 PR 进去，为什么说是？
不是，就是说 check it or not periodically。
哦，对，
对，
哦，对，就是说，但是你这个意思是说，要抓东西进去，
对，就是要确认说它有没有被存取到，
是否被
存取到。
你说这个被
对。好，
对，跟行业都有差别在。
就是说不定比较像是那个超连接这种感觉，就是那个叫什么来着？捷径，在 Windows 上面叫捷径。那捷径的话，基本上就是它其实是它会有一个 inverted 的一个的 pointer 是可以指到这个 inode 去，但它是分开两个 inode 去做管理。也就是说，这个档案它确实是一个档案，但它是一个它存的是一个超连接，连到前面那个人去。所以今天我举个例子来讲，如果原本档案被删掉的话，这个捷径就没用了，对吧？你今天做捷径，然后你把原本档案删掉就没用。那反过来，你今天如果是把捷径删掉的话，原本档案就还在。
因为我一开始实习，
对，这个是 softling 部分。harding 比较特别 ，harding 的概念是说，今天如果我看一下哦。对 ，harding 的意思是说，今天如果我想要做 harding 的话 ，actually 我会共用这个 inode， 然后 inode 里面会有一个 reference count， 所以我今天如果我把这个 harding 删掉，我不管是谁删的，就是复制的人删的，还是原本的人删的，他不会真的把档案删掉，因为他会有一个那个 counter 在这边做计数，知道说它是不是还有这个 link 存在。这样，也就是说 hard 就是比较像是实体定的感觉，那它主要用在 backup 做使用，因为你如果拿这个做 backup 的话，会有一个问题，你把这个做 backup，然后你把原本档案删掉就没了。那 harding 比较像是它 maintain 的各种版本，那每个版本都是有自己一个，就是一个 inode 那种感觉。就是我说的是有个 inode 是它会共用这个 inode，但它会有一个 reference number 去记录说现在有几个人可以去共用这个 inode。
就我刚刚问了两个，好，分享就是必须得好的解释，了解，就你没有到那么什么。就是这边是说，如果要比如说改一个 inode 的，比如说 file name 好了，那它等于是要新创一个 inode，然后再把那个 image 移到后面。
对。
那可是这样的话，比如说像这个的话，就是还是以这个为例哈，他把这个 image，那这边不是就有，因为这是在那个 storage device 里面嘛，这边是不是就会有
空洞？
对，那它是要怎么处理这个？
就是最开始说，就是 segment cleaning， 它会有一个 segment 单位去做 boundary collection。他就扫过去，然后知道你这边有空隙，然后他就把 没有空隙的资料，它就把有效资料先读出来，然后把它全部写到后面去，然后你这一整块就可以直接删掉。因为你现在有空洞，是因为你这边更新了。
对。
那你要把它空出来，它是可以做使用，因为在File system 来讲，在 LFS 来讲，它是一个 segment 一个 segment 去做使用的。所以它现在这块不能用，因为它里面有空洞。那一个简单解空洞方法就是我直接把它读出来，然后把它的有效资料把它写到另外地方去，就可以了。对。
我们就是让它几分做，你可能可以看一下左右要怎么讲。
大家先让后面。
老师那个什么，就是不知道最近 SS 不是很多 SSD 吗？那你有听说有什么file system可以就是针对 SSD 去那个有做什么？
我觉得如果是论文角度来讲的话，是蛮多了，就什么 F2FS 这种都，甚至是虽然 F2FS 是为了 Android 做，它其实它有对包括之前去做一点。
对啊，像 SLS 就是主要都在只听说在手机，
对，
就好像一般用 SSD 的人不会，
对，
就 Linux 电脑不会用。
没错。但是如果是研究，我觉得很多，但我觉得实际上其实还有一些问题，因为毕竟实际上来讲，大家不会只用 SSD。然后通常这种要跟 SSD 结合的包 system，通常都要吃一些 SSD 的 information。可是 SSD 厂通常不会愿意把 information 把它付给你包 system。所以就只这样，那个什么 tram 的指令可能是可以的，因为 tram 的指令是就是你从 file system 的 level 去做管理是可以。但你结果今天从下面传上去的话，通常我觉得会比较有。我觉得应该不是说技术难度，我觉得更像是各个厂商他自己的考量。
那这样你会觉得，如果他们结合起来，会效能更好？
结合起来效能一定会更好，对吧？对，只是说这个效能更好比例是不是值得这个厂商去做这样子的，就是设计这样子。对。
然后那个什么，之前我也对那个就是加密对硬碟加密蛮有兴趣的，就不知道现在就是我看有的是 SSD 它自己有加密的功能，还有人是坐在 OS 层上面的，对吧？所以就不知道这些东西他们。
我觉得比较像是它是不同群人在做，因为毕竟像刚才群人有说，就 Phison 他们那边主要是做 SSD 内部，所以他就谈到比较少作为系统，就是因为这两层是不同人在维护，所以我觉得它是关系到你今天想做这件事情是要谁发起来做。那技术上我觉得它不会有什么问题，就技术上两边的人都会做到，只是更多的问题是，那除了技术以外，这些其他第一考量，那应该要谁来做比较好？对，所以我就比较像这种问题。因为现在是 SSD 很强嘛，SSD 现在的 CPU 也都够有算力可以做这件事，所以我觉得它不会是太大问题。
确实，
对。
它现在很大部分的打工系统，就像 Windows 大家在用 NTFS，
对，
但是 Linux 像有比较新的，像 BTRFS 或者是 ZFS， 对吧？就好像就是就不知道现在写的这些打工系统是什么。就是那些 SD 会不会跑？
我觉得应该是说，这种新的档案系统它一定会有对某些部分做优化。可是那种优化通常都是要比较，就是就是你要去看说，就是这个档案系统专门用什么做优化，然后你就要把它闭在那个情境里面，它才真的有办法做优化。所以像 Windows 这种，它要布在哪里其实很难说，就它可能小到你可以布在你的 PC 这种，大到它也是可以当 workstation server 这种，所以它的应用的情境会挺广，所以它就会直接把它锁在他们自己客制化的一个档案系统里面。就像 Apple 也是啊 ，Apple 也是用自己的，它也不是用这些开源的，对啊，所以我觉得这个是，我觉得这也是关乎到使用者。对。
那个什么，我在想那个问问题是就是寄给助教，
对。
因为我之前有问，但我都没寄，
那就现在寄给他，对吧？
就那个有点给他回想一下。
好，没问题，
谢谢。
那所以问题比较单，我想因为就是
这里他把它
只要你不要
标记为整体之后，那它就是要什么才会区隔它，让它就是可以到它的 storage。
通常是周期性去做这件事情，就是他可能今天就两个状况，一种就是他可能累积太多资料了，然后就是把它写回去；另外一种他就是会设一个 timer，就是说可能几个 microsecond 就会去把一次去把它回写这种做，这个比较没有一定说他多久会去做。
所以这个是不一定的，所以
对
可能我自己写一个东西，让它可以主动去也可以
对，或者什么，你今天系统在一个比较轻漏的状态，我也可以做这件事情。
哦，所以这个就是不一定的。
对
哦，
对，没错。
我有一个就是